Assalamu alaikum, my dear students. How are you? Hope you will be fine and okay. I welcome you all into my today lecture. Our today lecture is about the wave nature of particle and the uncertainty principle. So let us start with the name of Allah Almighty. So Bismillah Rahman Rahim. Before going to start the wave nature of particle, I would like to recall your previous knowledge about the photoelectric effect, the Compton effect, and the pair production. And if you remember, I told you that those three phenomena are the experimental verification of the particle nature of radiation. Particle nature of radiation. Particle nature of radiation. I explain this to you that the way that is the radiation and particularly light, as I told, behave both as waves, such as in the young double slit experiment, as well as behave both as waves as well as the particle like photoelectric effect, the Compton effect, and the pair production. Right now, that is, we have another important topic, which is the wave nature of particle, and here we will explain the wave nature of particle here. The wave nature of particle. That there is associated waves with the moving objects, the wave nature with the moving objects. This is very important aspects, and this was first discovered, this effect was first discovered by Louis de Broglie, who was a French physicist and mathematician. Louis de Broglie. Louis de Broglie in 1924. His assumption was based on the fact that, according to him, there is associated, there is what? That there is associated wave nature with particles. With particle means with moving particles, okay? With the moving particles. With the moving particles, right? There is associated what? There is associated wave nature with the moving particles. They behave as that is that when the particle moves, they behave as waves also, or there is associated a wave nature with also, and it is based on the fact that, usually my favorite sentence, based on the fact that physics loves symmetry. That physics is very much symmetrical. If one thing is true, the opposite is true, and this is what you have seen in the previous topic, that for particle there was an antiparticle also. So according to the de Broglie, he said that if waves behave as particle. If radiation exhibits particle nature, then there must be associated wave nature with the moving particles, right? And this is what we would like to start from, how he explained this, that as you know that the Compton experiment show that the momentum of the particle is described by from the momentum from the momentum of the particle from the momentum of the particle we can write that the momentum of the particle p is equal to h lambda h by lambda. And this is what I think proved it to you also. If you remember, as I told, that we know that from the Einstein famous mass energy equation that E is equal to what? E is equal to mc square, if you remember. And then there I told that E is equal to mc into c, and then as you know E is equal to what? Pc. So P is equal to what? E by c. And you already know that according to the Planck relation, that E is equal to what? It is equal to h into f by c. And you already know that f by c is equal to 1 over lambda, so which is equal to h by lambda. And this is what I can get this from what? V is equal to f into lambda, since all radiation travel with the speed of light, so f into c. So c by f equals lambda, so lambda, so f by c equals 1 over lambda, if you remember this, right? So this is what I want to tell you. So this is what we have already learned from the previous expression. Now let us see that, as we all know that from this equation that p is equal to h by lambda, then this can be written as that lambda equals h by p. So for the particle, if we just do this for a particle of momentum, for the material particle or for the particle, we know that p equals p is equal to m into v. For example, let us say that if we have particle like extremely small particle, and if the particle travels with the speed v, then with this particle there will be associated momentum n into v. So the wavelength that is associated with the particle, it will be equal h by p, so h into m into v. So this is the wavelength associated with the particle. Wavelength, the wavelength wavelength associated with what? Associated with the moving objects, with the moving objects. Now here you see, look, I'm coming to that point right now, but first let me explain this to you. For example, if this is a particle, here you see, then with this particle, or as the particle move, then there will be associated wavelength also as the particle move. Now the question is that how to determine the wavelength that is associated with the particle, and we have definitely certain complication with this. And now what is that complication? I will revisit this thing here. Now you just know that the wave particle duality. For example, here you see that, look, that if we want to investigate the wave nature of the particle, for example, look, that the that wave can exhibits yeah, that is the phenomena of what? Interference or diffraction. Interference or diffraction. if we are capable to obtain the interference patterns with the particle as the particle moves or pass through a slit, then definitely we can experimentally prove that there is associated a particle nature with the a wave nature with the particle also. So here you see, look, as look at this here, as the particle moves, look, then there is associated what? Then there is associated the wave nature with the motion of the particle also, right? So we can obtain the phenomena of what? The phenomena of diffraction also. Here you see, look, as the particle moves, then this is what? The wave nature that is associated, the waves associated with the motion of the particle. If the particle travel with a speed v here. Now look how we can experimentally prove this. Look, we have the electron beam. This is the electron gun which generate the electron beam. And here you see that we have a graphite target or foil. And when the electron scatters from the graphite foil, then you will see on the screen the diffraction patterns. And you know, diffraction patterns can only be obtained from wave. So look, electron by itself is a particle, then there must be indeed what? There must be indeed a wave that will be associated with the particle. For example, look, you see from the Young double slit experiment, as you have learned from the YDS experiment, look, that if you shoot electron, right, then the electron beam, since they are particle, that at, at a time t, at a certain time t, right, from a point, the electron can only pass through what? Either through the slit S1 or through the slit S2. If you have an individual electron, for example, I will just, let me do it with a black. As you see, look, if you have the electron, for example, and if you if you have an incident electron, then the electron at a time can either pass through the slit S1 or the slit S2, just like the fact that since it is a particle and it cannot pass through both the slits simultaneously. And still you see here the maxima and minima. The diffraction patterns are the interference patterns, maxima and minima, as you see in the Young double slit experiment. So now look, electron being a particle, right? It cannot pass simultaneously through both the slit. For example, just like take the example of potato, right? That when you hit a slit with a potato, the potato can either pass through the slit S1 or the slit S2, and it cannot pass through both of the slits together. And so definitely it will have to hit only a single point every time you shoot the particle or the potato. But here is the case different. When you hit the potatoes, you find some hitting here, some hitting here, and some hitting here, which the classical mechanics predicts to be impossible. There is impossibility, right? That is, the particle cannot hit many points at the same time. It has to hit only one point since it can only pass through one slit. But here the story is different. So definitely there must be a wave associated, a wave nature associated with the particle, and then that wave nature associated with the particle like electron, it is then indeed measured and experimentally observed by David and Germer experiment, right, which is not the part your syllabus, or rather that is excluded from the syllabus. So this is what we can experimentally prove also. Now here, as you see, look, that as I told, that what is the problem here, that if, look, if I write this equation, since you know that h is a Planck constant which has value 6.63 into 10 raised to the power minus 34 joule into second, right, divided by m into v. Now, the complications are the bigger problems here. To problems to observe or detect the wave nature of particle, the wave nature of the particle. And what is that bigger problem? The bigger problem here is because of the extremely small value of what? The extremely small value of this h. That is that the wavelength will be so small, yeah, that will be so small that it is will be of the order of like this 6.63 into 10 to the power minus 34, and that will be very hard to detect, extremely hard to detect the wavelength associated with the common particle. For example, if you take the mass of the particle, just like for example that look, if you have mass 1 kilogram, for example, let us see that how, let me make it very simple. For example, you have a particle, and let for a particle with mass 1 kg and with speed even, let I will take the speed of a bullet, for example, around, and let I may make this is 100 meter per second. And then if you just see what could be the required wavelength, I just took the round number so that I can make the calculation very quickly and easily. So here you see log 6.63 into 10 to the power minus 34 joule into second. And here you see, look, what will be this mass? The mass is 1 kg. And here you see that it will be almost 100 into 100 into 100 meter per second. So here this wavelength will be equal 6.63 into 10 raised to the power minus 32 meter. So this wavelength is hard to detect, very are extremely small wavelength, extremely small wavelength, small wavelength, and this is hard to detect. This is what? This is very hard to detect. We cannot detect this wavelength. There is no instrument, right, invented which can detect the wavelength like this one. So this is why for the ordinary objects, even like a bullet, we there is associated the wave nature, but we cannot measure or detect the wavelength because of this extremely small number. So now what we can do, how we can observe this thing? You see here, look, that the wavelength is what? This wavelength is inversely proportional to the mass of the object for constant v, for constant v, and this wavelength is inversely proportional to the speed for constant mass, for constant mass m. So this is extremely difficult to observe because of this thing. Now, in order to make the wavelength what? To observe the wavelength of the, then what we will do, that is we use only lambda can be observed, observed for the particle, for the particle which has what? Which has extremely small masses, yeah, which have extremely, extremely small masses. Okay, the smaller the mass, then the more we will compensate for this factor, right? And we will be only able to observe the wave nature associated with this. And for this reason, usually we choose the particle like electron, since the mass of the electron is 9.11 into 10 raised to the power minus 30, minus 31, I think, yes, minus 31 kilogram. So this is very small mass, right? But contrary to this, or unfortunately to this, the electron speed is very high, and that is usually of the order of 10 raised to the power 7 meter per second, because the speeds should be small enough to make the wavelength large so that we can observe this. But even though with this extremely small mass, it is possible that we can observe the wave nature. And this is why I told that we use the electron scattering, or the diffraction of the scattering of the electron from a nucleus like graphite. And when the electron, the beam of the electron is scatter from this, and then we can obtain the diffraction pattern as I told. And the diffraction pattern from the electron can be obtained on the screen, showing this that there is associated the wave nature with the particle. And that is the most important result of this wave particle duality, or the wave nature of the particle, is the invention of what? The invention of the electron microscope. Electron microscope. And it purely works on this principle, which has a resolution 1,000 times greater than that of the optical microscope. So electron microscope is one of the uh, invention based on the wave nature of the particle. So here you have seen that there is associated wave nature with the particle, and there is a particle nature associated with the waves. This is known as the wave particle duality. But remember that we cannot observe both aspects of the the particle as well as the wave nature simultaneously. You cannot observe the particle nature of the particle as well as the wave nature of the waves, or light, or the radiation. For example, look at light. When light behave as a wave, then the its particle nature will be missing, right? And when the waves behave as particle, then the wave nature will be missing. For example, when wave exhibits the phenomena of interference, right, then at that point you cannot obtain the wave nature or the photoelectric effect from it. And when you are observing the photoelectric effect, then you cannot observes the wave nature, just like the interference. Why? Because in that case you wouldn't see any kind of reflection, right, or the bending of waves. Why? Because the photon will completely absorb, and you are available with nothing, right? So this is one of the reason that we cannot observe both aspects of the wave simultaneously. If you observe the particle nature, the wave nature will be missing. And if you observe the wave nature, the particle nature will be missing. Sometimes this is also called the Bohr complementarity principle, that we can only observe one aspect at a time, but cannot both at the same time. Right? So let us move on to the next. Now, our next topic is rather the final topic is the uncertainty principle. Uncertainty principle. It is one of the most important result of the wave particle duality also. What does the uncertainty principle states? The uncertainty principle states that we cannot measure, that it is impossible, it is impossible, it is impossible to measure both the position, both the position and the momentum and the momentum of the particle it together, it is impossible, it is impossible to measure both the position and the momentum of the particle precisely precisely at the same time or simultaneously at the same time. This is known as the uncertainty principle, right? Or the Heisenberg uncertainty principle, who was a German physicist, and he described this important principle which is based on the wave nature of the particle. Here you see that, look, that is, if there is what, look at this particle, there is, as the particle moves, right, then there will be associated what, there will be associated momentum with the particle. P is equal to mv, and then there will be the position of the particle also, right, that delta x, position of the particle are like this delta x, for example, that where the particle will be likely to found it at certain instant of time where the particle is. So according to the uncertainty principle, if you measure the position of the particle precisely, then you will lose on momentum, right? There will be uncertainty, greater uncertainty in the momentum. And if you measure the momentum precisely, then you will lose on the position, right? There will be uncertainty in the position of the particle, right? It will be, there will be a greater uncertainty that where the particle could be. Now according to this uncertainty principle, that the momentum and the this uncertainty in the momentum and the position of the particle, the product of the momentum and the position of the particle is to h cut to h, that is the uncertainty in the position in the momentum is, for example, look, if you want to measure the position of the particle or the momentum of the particle, then the uncertainty in the position will be like equal to Planck constant. It will be of the Planck constant. Right now, why? Let us see that, for example, as I told, if you want to observe this, the position of the particle, as you see, look, then definitely, for example, if you want to see it, this particle, as the particle is moving, then who is carrying the information with you? Of course, it is the light which you are using to detect a particle. For example, if you want to see the electron, then definitely the information being carried to you by what? Light. Means that light means a photon. So if you want to calculate the position of the particle, then if the particle moves, then definitely there will be uncertainty in the position of the particle. That uncertainty will equal to the wavelength of the light used. Now what is this lambda? This lambda is the wavelength of the light used, yeah, radiation used. So definitely, because you know that it is the light which carry you the information. For example, if you want to see something, definitely you will use the light, will come, it will reflect and will come back to you. So definitely the light that which you use or which carry information to you, since when it strike this and then come back to you, then definitely it there will be what there this the light consists of photons, and photons have a wavelength lambda. So in order to describe the position of the particle, then the position of the particle have the uncertainty equal to the wavelength of the light. So let's see, this is my equation number one. And here for the momentum, as we already know that the momentum of the particle, that have, then this equals to Planck constant h by lambda, right? Now this is equation number two. So from 1 and 2, So from 1 and 2, we can write that the product of this position and delta P equal what? It is equal to H into lambda. And you see that this lambda and this lambda get cancelled. And what happens? Delta X into delta P equals the Planck constant, right? So now look, this is so interesting equation, so important equation. For example, look, here I just want to explain it to you separately, okay, because this part is sometimes difficult for the student. Here you see, look, delta X equals lambda, right? The order of the lambda. And here you see delta P into H by lambda. Now look, if you want to measure position, position can be precise. Position can be measured what? Can be measured precisely. If lambda is very small, is very small. That is, if you use light of extremely short wavelength. So look, the smaller the wavelength, the more precision will be in the position. But at the same time, this is what the momentum is, the uncertainty in momentum is inversely proportional to the wavelength. So if you make the wavelength smaller, then what will happen? Lambda becomes smaller, so the uncertainty in the momentum, which is delta P, it will become greater, right? So this is the problem. But here, if you want to measure the momentum precisely, what you will make? You will make lambda very large. So by making lambda very large, delta X will become large. So there will be then greater uncertainty in the position of the particle. In the same way, for example, look, by making, what does this means? For example, look, if you have a particle, let's say this one, for example, look, that if you make the wavelength large, right, to calculate the momentum precisely, then what will happen? Look, when you have this big lambda, and for small lambda here, what I would like to see here, like this one here. Now this will be so easy. If you just look here, I want to explain it to you from here. Now let us see. Look, this is the wavelength here, right? And here you see the wavelength. For example, look here, this is the wavelength. This is what you give you precise what? Precise position, but less precise momentum. Less precise momentum. Here, what you see, that precise momentum, but less precise position. Precise position. And I will tell you this how. And let us see that if you look, this is very easy. Look at this wavelength. This wavelength is so large. And here, look, what is this wavelength? Very small. Now look, finding something in a bigger room is easy, or finding something in a small room is easy. Of course, in the small room. So here you see that the probability of the particle to be found expands over a larger distance, as you see. So it is very difficult that to find the exact position of the particle. That instant it might be somewhere here, somewhere here, somewhere here. So the probability you see is very less. But here the probability of finding the particle is very large. Why? Because this is very small region, right? And the particle can be easily located within this region. So this is what the uncertainty principle is. For the macroscopic level, the uncertainty principle are not that much important, but for extremely small particle are on the nuclear scale, the uncertainty principle is very important. And there are many things, but one important result I would like to tell you that the uncertainty principle can very easily, it is the uncertainty principle. The uncertainty principle, it is the uncertainty principle which can tell us that why electron, and the uncertainty principle can tell us that why electron cannot, the uncertainty principle tells us that why electron cannot exist inside the nucleus, cannot exist inside the nucleus. Sometime you might think why electron cannot exist in the nucleus, and we can use this principle. Why? Because if you just see, look from the uncertainty principle, delta x, right? Delta x into delta p equals h. Or what we can write from this principle, that momentum of the particle h into delta x, or this is m into delta v h into delta x. Or look, we can say that delta v is equal to h m into delta x. Now you see, look, what is this m? For example, it is the mass of the electron. What? The speed of the electron. The speed of the electron. In order to find the electron to be inside the nucleus, what speed it could be? And this is what? This is the size of what? The size of the nucleus, if you want to find it in the nucleus. And if you want to find it in the atom, then this will be the size of the atom. And indeed, look, uh, this velocity of the electron, it comes after calculating. For example, if you just use the size of the nucleus, for example, look here, if you just want to find, for example, look, if this is the nucleus like this, right? So this is delta x, the size of the nucleus, or the radius of the nucleus, I think, which is 2 into 10 to the power minus 14 meter. And I'm sorry if I do not remember by heart, right? The mass of the electron, you know, as I told, the mass of the electron is 9.11 into 10 to the power minus 34 kilo, oh sorry, minus 31 kg. So if you just do all this calculation, the Planck constant 6.63 into 10 to the power minus 34 joule second. So if you put all these values, delta V will come out to be of the order of what? Of the order of 10 raised to the power 10 meter per second. And you already know which is not possible. Which is what? Which is not possible. Electron with this speed cannot be observed, since no material particle can travel with the speed greater than the speed of light, not even with the speed of light. Don't speak about this, right? This is very far from okay, so no particle can travel with this speed. So in order for the electron to be inside the nucleus, it must travel roundabout with the speed of the order of 10 to the power 10 meter per second, right? Which is impossible. So therefore electron cannot be inside the nucleus. But if you want to look at for the electron inside the atom, then their speed came out to be the order of 10 to the power 7 meter per second. And electron with these speeds are observed, right? So electron can exist within the atom but cannot exist inside the nucleus. There is another form of uncertainty principle also, another form of uncertainty principle, and that is about what? The energy of the particle, the energy associated with the particle, that will be equal this into the energy of the particle, the time t, and that uncertainty is equal to the Planck constant. And you can now study this by yourself also. This is just like in the same way. So uncertainty principle is applicable on the nuclear scale only, and we have to take it into account. So uncertainty principle tells us that it is impossible to measure the wave, to measure the position as well as the momentum of the particle precisely at the same time. This is impossible. If you measure the position precisely, you will lose on the momentum, and if you measure the momentum precisely, you will lose on the position. And this is the experimental fact, right? And it is just because of the wave particle duality, right? So this is the end of the unit 18, and inshallah we will then start the last unit in the coming lecture. Okay, so thank you for a while now.